Somewhere at the very edge of what we can see drifts a small, dark, distant world we still barely understand. This is one of the very first images ever taken of that world, captured in November 2003. Her official name is Sedna, after an Inuit sea goddess who lives at the bottom of the frozen ocean. Past everything we thought we knew, past Neptune, past the last of the classical planets, lies a frozen graveyard. Sedna was found from here, the Palomar Observatory in Southern California, on a routine sky survey. Using this telescope, the Samuel Ocean Schmidt telescope, which for a while was one of the most productive discovery tools we had. The team behind the discovery was led by Mike Brown, an astronomer at Caltech. Just 2 years later, in 2005, the same team announced Eris, a world slightly larger than Pluto itself, and Makemake, another distant dwarf world, its surface tinted red by ancient methane frost. And out there, one by one, we have found worlds too strange to belong to any explanation we already had. In 2016, Konstantin Batygin, a theoretical astrophysicist at Caltech, sat down with Mike Brown to run the numbers. Some of them we have not yet actually seen, and one of them we may not know exists at all. But their orbits point somewhere, 6 of them at least, tilted the same way, as if by design. As though something enormous, hidden, patient, has been quietly pulling on them for a very long time. NASA's WISE and NEOWISE space telescope scanned the whole sky in infrared for warm objects. The Blanco telescope in Chile carries the dark energy camera, a wide-field digital survey instrument. The Subaru telescope in Hawaii, one of the largest single-mirror telescopes ever built. And now the LSST camera, the largest astronomical camera in the world, weighing 3 tons. Installed at the Vera Rubin Observatory in the Chilean Andes, which began its first surveys in 2025. And whatever it is, if it is anything at all, is still out there, waiting to be found. The story of Planet 9 really begins here, at the outer edge of our solar system, past the orbit of Neptune, in a region we thought we understood. And there was much more out there than we ever imagined. What we found, quietly, over the past 20 years, was that some of these distant, icy worlds don't behave the way they should. The idea of a belt of frozen bodies past Neptune was first proposed by Gerard Kuiper in 1951, a decade before anyone confirmed it existed. For half a century, it remained mostly a prediction, a mathematical suggestion of what should be out there, waiting for us to look. Then in 2005, Mike Brown's team at Caltech announced the discovery of Eris, a distant world slightly larger than Pluto itself. The find was so significant that within a year, the definition of the word planet was rewritten, and Pluto was reclassified as a dwarf. Before Eris, there had been Quaoar in 2002, a gray-brown ice world with surprising thin rings that no one had predicted. One by one, over just a few years, the outer solar system started giving up its hidden inhabitants. Makemake was announced in 2005, a reddish-brown world of methane ice, roughly 2/3 the size of Pluto. Each new discovery pushed the map of what we knew a little further outward into the dark. Haumea spins so fast it has stretched itself into an egg. In just a few years, 5 new dwarf-scale bodies had joined the roster of what lived out past Neptune. And around Pluto, they even found Charon, so massive that the 2 of them wobble around a common point out in space. For a while, the pattern looked almost too tidy. A family of icy worlds obeying gravity, doing exactly what they should. That impression came from long nights at Palomar Observatory in California, where the systematic surveys ran for years. Night after night, the telescopes tracked slowly across the same fields of sky, waiting for something to reveal itself. Then in November 2003, the same team spotted something they could not quite make fit. It was small, deep red, and its orbit did not make sense in any reasonable model. The technique for finding worlds this far out is older than the space age, and beautifully simple in principle. You take one image of a patch of sky, then another a few hours or a night later. You subtract one from the other, and anything that moved against the fixed stars stands out plainly. It's called the shift and stack method, and it has revealed nearly everything we now know past Neptune. But Eris was different. It wasn't the technique that mattered so much as the sheer size of what they had found. Eris was bigger than Pluto, and it forced astronomers to reconsider what the word planet even meant. Even comets carried whispers about what shaped the outer edge of the solar system. Elegant, patient, indifferent to whether we ever noticed them at all. Close to the sun, some worlds could be violent and molten, like Jupiter's moon Io. But past Jupiter, past Saturn, past even Neptune, that warmth vanishes almost completely. In the deep outer solar system, everything freezes, and everything drifts slowly around a distant, faint sun. At Cerro Tololo and other observatories, the surveys continued through the 2000s and into the 2000s, and into too slowly, in fact, to have come from anywhere in the region we had already mapped. Its perihelion, the closest it ever came to the sun, sat at 76 astronomical units. That's 76 times farther from the sun than Earth, more than twice as far as Neptune ever gets. And its farthest point stretched to nearly 1,000 times the Earth-Sun distance, an orbit stretched to impossibility. Whatever formed Sedna, or threw her into that orbit, had to have been something extraordinary. Neptune's gravity was not enough. Sedna never comes close enough to be affected by any known planet. So something had to have bent her path long ago and left her locked out there in the deep. But when we looked for a nearby cause, there was nothing at all. From Sedna's orbit, our sun is just a bright star among many, not a warm disk in the sky. Pink hydrogen light glows softly across half the visible sky. Then, slowly, others like Sedna began to appear in the archives, worlds no one had noticed the first time through. Buried in old plates and stacked exposures, moving too slowly for casual detection, they waited quietly. In 2014, a team led by Scott Shepard announced 2012 VP113, nicknamed Biden for the letters in its designation. Its orbit was even more extreme than Sedna's. Perihelion at 80 astronomical units, aphelion far beyond. And out past the Kuiper belt lay the truly cold, truly distant realm called the Oort cloud. A hypothetical spherical shell of comets extending nearly halfway to the next star, where the sun becomes just a light. Whatever bent Sedna's path, whatever bent VP113's, was neither known nor visible in any of our maps. Somewhere, astronomers began looking at those numbers together and asking whether they were seeing a pattern at all. Could random noise, drawn from a small sample of discoveries, create a pattern this striking? Patterns had fooled astronomers before, and everyone knew to be suspicious of coincidences. But then Gong Gong was confirmed. Another distant, red-gray world, its orbit tilted the same way as the others. Its perihelion clustered near the same angle. Its plane matched the growing family, its aphelion far away in the deep. And it was as though these worlds were all being nudged by something none of the telescopes could see. Astronomers checked every possibility they could think of: observational bias, small sample statistics, hidden selection effects. All 6 of their orbits leaned the same direction in space. The statistical odds against pure coincidence began to climb, hundreds to 1, then thousands to 1 against. The outer solar system had been reshaped by ancient events we already knew. Triton was captured by Neptune long ago. Perhaps some of these bodies had been thrown outward by an early close encounter, back when the sun was young. Maybe a passing star had grazed the solar system billions of years ago and left behind a lingering scar. Maybe a rogue body had briefly joined and left again, dragging orbits along with it. But the pattern did not fade with time, and it did not fit neatly with any known ancient encounter. 5 objects, then 6, then 7, all pointed the same direction, all tilted the same way. The pattern held, and the search widened, and telescopes turned to look further out than ever before. Titan. One of the most familiar mysteries was long known, a thick orange atmosphere unlike any other moon. But out beyond even the Oort cloud, what could possibly be shaping so many orbits at once? Something with mass enough to reach across billions of miles of empty space and hold it. Sedna, the coldest known world, drifts on quietly, alone. The ancient star clusters still burn quietly across the sky, older than the sun by billions of years. Even small ice worlds close to home speak in their own ways. Enceladus spits water into space. But it was empty space itself that was raising the strangest question of them all. Then Orcus, sometimes called the anti-Pluto for its mirrored orbit, fell into the same pattern too. Its perihelion clustered in the same direction, its plane tilted the same way. Another vote for something invisible. When astronomers plotted the 6 orbits together, the picture was striking, all pointing to one quadrant of the sky. The alignment held across billions of miles, across orbital periods of many thousands of years each. And every single one of these worlds tilted upward from the plane of the classical solar system in the same way. Astronomers began to whisper a possibility that would once have sounded outrageous to say out loud. A large planet, hidden in the deep outer dark, pulling on these worlds across immense distances. Not Earth-sized, much larger, maybe 5 to 10 times Earth's mass, an unseen Neptune-scale world. Some of these questions can only be asked slowly, indoors, by 2 people. The ones who did the math worked late, on paper and screen, with maps and models of thousands of simulated orbits. As the models ran and the simulations converged, the idea slowly stopped feeling like speculation. 6 known worlds now agreed on one quiet, insistent fact. Something else was out there. From 400 astronomical units away, our own sun would appear as an impossibly small point of light. The astronomy community responded quickly, and observers around the world turned their telescopes outward. Some proposed alternatives, a small primordial black hole capture perhaps, instead of a planet. A patch of sky that never seems to quite change. But the gravitational effect was there, and it was consistent, whatever was causing it. The search intensified, and archives were re-examined, and new deep surveys were designed specifically to hunt for it. More extreme trans-Neptunian objects were cataloged, and most fit the pattern the earlier 6 had already suggested. Telescopes at ground level and in orbit turned their attention outward, hunting the quadrant where the planet should live. New missions were proposed, new detectors considered, all reaching toward the same silent, distant question. One eye, patiently watching from the remains of a dying star. Sedna, meanwhile, continued her long, slow 7,000-year orbit, indifferent to our new questions. The sky held its answer somewhere out there, in a direction we now roughly knew, but not exactly where. Somewhere in a place no one had checked with the right instruments, or with the right patience. And a pattern like that does not appear in a chaotic system unless something is holding it in place. Which brings us to a question 6 scientists sat down to work out in earnest. Is there really something out there? Their names were Konstantin Batygin and Mike Brown. And by the winter of 2016, they had spent almost 2 years quietly running the same calculations again and again. Batygin was a theoretical astrophysicist, Brown an observational one. Together, they were unusually well suited to look at what these 6 clustered orbits actually meant. They had run tens of thousands of computer simulations of the outer solar system, testing different arrangements of unseen mass at different orbital distances. And what kept surviving the simulations was a specific kind of world, not Earth-sized, not gas giant-sized, but somewhere unusual in between. A quiet, massive world that no one had ever seen. They published their result in the Astronomical Journal on January 20th, 2016, and it landed with more weight than either of them had expected. Their proposed body, they wrote, was roughly 5 to 10 times the mass of Earth, a super-Earth, or a small Neptune-class world. Its orbit, they estimated, was extremely elongated, ranging from around 200 astronomical units at perihelion to 700 or more at aphelion. A single orbit at that scale would take somewhere between 10 and 20,000 Earth years to complete once. They called it, cautiously, Planet 9, a name deliberately understated for a claim as large as it was. The paper did something clever and rigorous. It made specific numerical predictions that other astronomers could test. If their planet existed, it would sit in a certain quadrant of the sky, at a certain range of distances, following a certain orbital plane. Astronomers, for the first time, had a specific place to look. For comparison, Uranus and Neptune, the two known ice giants, each sit around 30 astronomical units from the Sun. Planet 9, if it exists, would be much smaller than Uranus or Neptune, but many times farther away and much colder. Its surface temperature would be somewhere near 40 Kelvin, only 40 degrees above absolute zero, colder than anything else regularly discussed as a planet. From its position, our own Sun would appear as one bright star among many, not as a warm, illuminating disk. The gravitational pull that Planet 9 would exert on the outer solar system was small on the scale of the whole galaxy, but enormous compared to nothing at all. That pull, working over billions of years, could explain the entire alignment pattern of the 6 known clustered objects. It could also explain a few other odd features of the outer solar system that had never quite fit any earlier theory. That was the strongest part of the argument, a single hypothesis that seemed to explain multiple unrelated puzzles at once. A rare and quiet kind of elegance in a science paper. Sedna, of course, remained one of the strongest markers of the case, her extreme orbit being one of the earliest hints that led here. Objects like her had been described one at a time for years, each one a curiosity, none quite fitting the classical picture. But when 6 of them were plotted together, and none pointed in the direction that random chance would predict, the case built itself. The paper did not claim to have found the planet, only to have argued that something planet-shaped almost had to be there. The proposed orbit was so elongated and so long that Planet 9 would spend most of its time in the very darkest, coldest regions of the outer solar system. When astronomers began pointing telescopes at the predicted region, they were searching for an object dimmer than almost anything else observed at solar system distances. Sedna, at her extreme distance, is roughly 100 million times dimmer than the faintest star visible to the unaided eye, and Planet 9 could be dimmer still. That is why the world was still hidden even after decades of survey work, if the world exists at all. The scale of what a serious search meant now shifted significantly, even for well-funded professional survey astronomy. Observatories at Palomar and Mauna Kea and Cerro Tololo all began dedicated searches of the predicted quadrant. The dedicated wide-field telescopes on Earth were pushed to their sensitivity limits, looking for a slow, faint, cold body. The Wide-Field Infrared Survey Explorer, WISE, had already ruled out anything Jupiter-sized within a light-year of the Sun. So Planet 9, if it exists, has to be smaller than that, in the ice giant mass range specifically. From the Sun's perspective, Planet 9 would sit somewhere in a quadrant of sky roughly the size of a spread hand held at arm's length. But hidden inside that hand, an entire ocean of dark. The 2012 VP-113 discovery itself had come at almost the edge of what Shepard's team's instruments could see. Each new object at the extreme edge required years of dedicated telescope time and careful follow-up to confirm. As more extreme trans-Neptunian objects were cataloged after 2016, most of them continued to fit the clustering pattern the original 6 had suggested. Not every single new discovery matched, but the majority did, and the odds against random arrangement stayed strong. By 2019, Batygin and Brown updated their published estimates, a slightly smaller mass than first proposed, a slightly closer orbit. Around 5 Earth masses they now suggested, and a semi-major axis of around 400 astronomical units. That would place Planet 9's average distance at roughly 400 times the Earth-Sun distance. Still deeply cold, still deeply dark. The prediction was refined, but its central claim held. Something invisible, moderately massive, was shaping the outer solar system. The astronomy community was not universally convinced, though. Some of the response was thoughtful skepticism. One counter-hypothesis suggested that the clustering could be an artifact of where we happen to have looked for these objects. A ghost hiding inside how we've chosen to look at the sky. In other words, the pattern might not be real out there. It might just be what we see because of where and how our surveys have pointed. A 2020 study led by Kevin Napier and Fred Adams argued this case, and it landed with real weight in the field. But when researchers examined the specific extreme TNOs more carefully and modeled the exact biases of the actual surveys used, the pattern held even with those corrections. As more observational data accumulated, more precise statistical analyses have generally continued to support the case for something out there. There were other alternative ideas too, some of them stranger than a hidden planet. Jakob Schultz and James Unwin proposed in 2019 that the missing mass might not be a planet at all. It could be a primordial black hole, a small, ancient black hole formed in the earliest moments of the universe, no larger than a bowling ball. Such a black hole, if it existed, would still exert gravity like a planet of similar mass, but be completely undetectable optically. The idea sounds exotic, but it is not physically absurd. Primordial black holes are hypothesized to have formed under specific conditions in the very early universe. One way to search for such an object would be through gravitational lensing, the way its mass would subtly bend background starlight. That method requires enormously precise measurements, though, and no strong candidate lensing signature has been reported so far. In 2022, the astronomy community also considered whether the perceived pattern might be simply a small sample effect. Too few objects to draw a strong conclusion. Small samples of anything can play strange tricks with statistics. New surveys, new discoveries, and continued statistical work would, over the years since, either strengthen or weaken the original clustering claim. So far, on balance, the case has held rather than collapsed, though it has neither been proven nor ruled out completely. There is a real, ongoing scientific conversation about whether Planet 9, as originally proposed, truly exists. That conversation happens through papers and conferences and long email threads between astronomers on 3 continents. It happens through decades-old survey archives being re-examined with new statistical techniques, and through new dedicated searches at some of the largest and most sensitive telescopes we have ever built. Meanwhile, the objects that started all of this, Sedna, VP-113, and their fellow extreme wanderers, continue their slow, silent orbits, indifferent to our questions about them. They will still be out there tomorrow, and next year, and centuries from now, whether Planet 9 is real or not. The precision of Planet 9's predicted orbit is roughly enough to say where to look, but not exactly where within a very large search zone. That search zone, in sky area, is many thousands of times larger than the disk of the full moon. So it takes enormous amounts of observing time to systematically comb through it, even with a well-funded modern survey. Slow, patient work, one clear night after another, over years. The Zwicky Transient Facility in California, the Dark Energy Survey in Chile, various campaigns at Subaru, and others have all contributed candidate hunts. Individual candidates have popped up occasionally, brought public attention, and then been ruled out on follow-up. False alarms are part of the process. But nothing has yet been observationally confirmed as Planet 9 itself, not through any of these campaigns. The waiting has stretched, quietly, from months in 2016 into years, and now into most of a decade. In that time, Sedna has moved measurably along her enormous orbit, closer now to her perihelion than she was when Brown's team first found her. She will actually reach her perihelion in the mid-2070s, and become a great deal more accessible for study for a brief cosmic moment. The astronomers who first found her will not, most likely, be alive to see that closest approach. But the field they built will be, and it will be watching. Meanwhile, the region of sky where Planet 9 is expected to sit remains, from our vantage, almost entirely uneventful. The stars there look the same as any other patch of sky. No hint that anything remarkable might be drifting invisibly through it. A large planet at 400 astronomical units distance would be, from our perspective, roughly the apparent brightness of an average small comet, if we happen to look at exactly the right place. A single very faint point somewhere in a sky of many millions. The search continues at multiple observatories, on both hemispheres, using increasingly sensitive equipment as time passes. In 2024, the Subaru telescope's Hyper Supreme Cam camera was used to run particularly sensitive deep surveys in the predicted zone. Similar surveys were also being run with the dark energy camera on the Blanco telescope in Chile. As of the current time, no confirmed detection of Planet 9 has been made by any of them. The absence, in itself, has become useful information. Each survey that comes up empty rules out certain regions and certain brightness levels. Even the long silence is telling us something now, quietly. By now, the case for something out there, whether Planet 9 or something else, has become one of the most closely watched open questions in modern astronomy. The 6 original clustered objects have grown to more than 20 extreme TNOs of varying quality of measurement. Some of them fit the pattern beautifully, others less so, and the statistical case is refined with every new discovery. The best evidence remains, as it was in 2016, indirect, the gravitational fingerprint rather than the object itself. And yet the question keeps drawing people back, because a discovery this large would rewrite our sense of what our own solar system actually looks like. For most of history, the map of the outer solar system had a comforting sense of being nearly complete, at least in broad strokes. Planet 9, real or not, has already broken that comfort. The map has an open question drawn across its outermost edge. And the answer, so far, has still not come to us. Which brings us to the biggest new instrument in astronomy, and to the observatory that may finally end, one way or the other, the search. The biggest astronomical instrument to come online this decade sits high in the Chilean Andes, on a mountain called Cerro Pachón. Its name is the Vera C. Rubin Observatory, and it was designed for exactly the kind of question Planet 9 represents. Vera Rubin herself was one of the most consequential astronomers of the 20th century, and the observatory carries her name for good reason. In the 1970s, she measured how stars move within galaxies, and found that the outer stars moved much faster than they should have. That work led directly to the confirmation that dark matter exists, invisible mass shaping visible motion. So an observatory named after her, hunting for another kind of invisible mass shaping visible motion, is a fitting tribute. The Rubin Observatory sits at 2,682 meters elevation, above most of the atmospheric turbulence that softens ground-based observations. It has been under construction, in one form or another, since the early 2010s. The main telescope is called the Simoni Survey Telescope, named after donors Charles and Lisa Simoni. Its primary mirror is 8.4 meters across, an enormous polished piece of glass shaped for a very specific job. The whole optical assembly is designed for one purpose above all: surveying vast amounts of sky quickly. Attached to it is the LSST camera, the largest digital camera ever built for astronomy. It has 3.2 billion pixels arranged across an array roughly the size of a small car. Each single exposure it takes shows a piece of sky larger than 40 full moons stacked together. One night of observing, and it will collect roughly 20 terabytes of astronomical data. By the standards of previous surveys, that number is staggering. Over the 10 years of its planned Legacy Survey of Space and Time, or LSST, it will accumulate around 500 petabytes of images. That data will be processed through custom pipelines developed over years of preparation. The result will be a moving picture of the whole visible sky, taken again every few nights for a decade. That kind of repeat, wide-field coverage is precisely what a search for a slow-moving, distant world requires. Between exposures a few nights apart, a Planet 9 at 400 astronomical units would move by a small but measurable amount. Enough that it would show up as a moving point of light against the fixed background stars, exactly the way early TNO discoveries were made. The advantage now is scale. Instead of a small team squinting at one photographic plate at a time, algorithms will scan billions of pixels. The observatory expects to catalog around 40 billion astronomical objects in total across its full survey. That is more than has been cataloged in the entire prior history of astronomy combined. Among those objects, tens of thousands are expected to be new trans-Neptunian bodies, most of them far too faint to have been noticed before. Each new TNO adds to the statistical picture of what the outer solar system actually looks like. And each new orbit is another test of the clustering pattern that led to the Planet 9 hypothesis in the first place. If the pattern holds up as the sample grows, the case for something invisibly massive out there strengthens. If the pattern dissolves as more objects are found, the case weakens, and something like an observational bias explanation gains ground. Either outcome, sharply, would be the most important result the search has produced since 2016. The observatory's first light, its earliest test image, was captured in October 2024. Full science operations began in the first half of 2025. In the earliest published results, the observatory was already discovering thousands of new asteroids and trans-Neptunian objects per night. None of them, so far, has been identified as Planet 9. But it is still very early in the 10-year survey, and the observatory has not yet finished scanning the specific quadrant of highest interest. Each night that passes brings the search that much closer to a definitive answer. One way or the other, the 10-year LSST survey is expected to be conclusive. Either it will find the planet, or it will rule out its existence at the mass and distance the hypothesis predicts. A negative result would not be a failure. It would be a clear scientific finding, and it would send astronomers back to explain the clustering pattern by some other means. A positive result would be one of the largest planetary discoveries in modern astronomy. There are also researchers keeping their focus on the alternative hypotheses, in case Planet 9 itself is not there. The primordial black hole hypothesis has continued to evolve since Schultz and Unwin first proposed it in 2019. It could not be detected by any optical survey, since a small black hole reflects and emits no visible light. But it might be found gravitationally, through the way its mass would microlens background stars if it drifted into alignment. Some researchers have proposed specific microlensing signatures a small primordial black hole would produce. So far, no strong candidate signature has been detected in the archives. A more subtle possibility, sometimes discussed, is that Planet 9 was captured during the Sun's very early history. The Sun was born inside a dense stellar cluster, roughly 4.6 billion years ago. In that early environment, close encounters with other young stars were common. A large planet from another star could have been gravitationally exchanged into our own solar system during one of those passages. It would then be a captured world, not one that formed here, and its outer, tilted orbit would be a natural consequence of its history. This capture hypothesis fits some of the observed features of Planet 9's expected orbit rather well. It is speculative, though, and would be difficult to distinguish from a solar system-formed body once the planet was actually found. There are also simulations that suggest Planet 9 might not be a single body at all, but a diffuse ring of many small bodies exerting collective gravity. Such a ring would be even harder to detect directly, though the observational effect on TNO orbits would be similar. As with much of astronomy, the theorists have generated many candidate explanations, and observation slowly narrows them. Meanwhile, the numbers in the extreme TNO catalog continue to grow year after year. The original 6 clustered objects, from 2016, now number more than a dozen well-observed extreme TNO orbits. Most of the newer discoveries fit the clustering pattern, a few do not. The statistical case has been debated in every direction. Proponents update their models, skeptics update theirs, and the field converges slowly. For the general public, that slow scientific back and forth can be frustrating. Big announcements of certainty are exciting, but real progress on hard problems often looks like this instead. Gradual, careful, patient work over many years. The Vera Rubin Observatory represents an inflection point in that slow work. For the first time since 2016, a single instrument has both the sensitivity and the sky coverage to move the question from open to closed within a definite time frame. That is not a small thing in astronomy, where major questions have historically stayed open for generations. In many ways, the search for Planet 9 echoes an older search, the search for Neptune itself, back in the 1840s. Astronomers then noticed that Uranus was not following its predicted orbit precisely. The deviations were small but real, and they hinted that something was gravitationally tugging on it from further out. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unseen planet should be. Le Verrier sent his prediction to the Berlin Observatory, and in September 1846, the astronomer Johann Galle pointed a telescope where Le Verrier had said. Within an hour, Neptune was found, just about where the calculations said it would be. It remains one of the great triumphs of physical reasoning applied to observation. Whether Planet 9 will follow the same pattern remains to be seen, but the parallels are hard to ignore. In both cases, the argument comes first from the motions of visible objects, and only later, if at all, from the direct sight of the hidden mass. The 19th century calculations were about a planet 3 billion miles away. The Planet 9 hypothesis is about a body 10 times further out again. That may be one reason the current search has taken so much longer than the search for Neptune did. Sedna and VP 113 and their fellow extreme trans-Neptunian objects will still be there, unmoved by whatever we find or fail to find. Their long, slow orbits do not depend on our understanding of them. They will still trace out their vast paths, quietly, whether Planet 9 is real or not. In that sense, the search for Planet 9 matters more to us than it does to the outer solar system itself. Every hypothesis, whether right or wrong, is a chance to sharpen our own picture of what our home system actually looks like. For most of history, our map of the solar system had 8 rocky and gas giant worlds, and a lot of comfortable emptiness beyond them. The last 20 years have turned that emptiness into a rich, populated, still only partly mapped frontier. The confirmed discoveries alone, Eris, Makemake, Haumea, Sedna, VP 113, Gong, Orcus, and others, already redrew our sense of the outer edge. A Planet 9 would redraw it again, and would place a large planetary body in a region we had assumed for centuries was essentially empty. Whether we find it in the next decade or the next century, the story will not end at any single result. There are almost certainly other surprises out there. Objects we have not seen yet, orbits we have not measured yet, patterns we have not noticed yet. The outer solar system, at its distances, is essentially a vast, dark reservoir that we have only just begun to sample. Some of what we find in the next decade may reshape our sense of how the whole solar system formed and how it settled into its current configuration. Every new distant body carries some information about that history in its orbit. The gravitational fingerprints of past encounters, past migrations, and past disturbances are all preserved out there. Reading them requires patience and precision on scales that the pre-LSST era could not routinely provide. That is what the next decade of astronomy is uniquely positioned to do. Vera Rubin herself, who did not live to see the observatory named after her come online, would have appreciated the arc of it. Invisible mass, shaping visible motion, patiently uncovered by careful measurement. Her scientific work was ultimately about paying attention to small, systematic disagreements between prediction and observation. That instinct is what led to dark matter, and it is what led, later, to the Planet 9 hypothesis. In many ways, it is the animating instinct of modern astronomy as a whole. Small deviations from what we expect, taken seriously, can reveal enormous hidden truths. And that, more than any single planet or particle, may be the most enduring thing the search will teach us. Vera Rubin's method, paying attention to what should not be there, has shaped astronomy in more ways than one. Every year, some new invisible influence gets caught in the same way that dark matter was first caught, by its measured effects on visible things. The universe, it turns out, is full of things that are only detectable through what they pull on. Dark matter itself was named for that quality. It does not shine, but it holds galaxies together against their own rotation. It outmasses ordinary matter by a factor of about 5-to-1 in the universe as a whole. Most of the mass in the observable universe is not the kind of matter that stars and planets are made of. It is something else, whose only fingerprint is gravitational. That thinking, that there could be enormous mass we cannot see, sounded strange in the 1930s when it was first proposed. The Swiss astronomer Fritz Zwicky suggested it in 1933, studying the motions of galaxies within the Coma cluster. He found their speeds were far higher than could be explained by the visible mass alone. He called what he saw Dunkel Materie, dark matter, and the idea sat quietly for decades. It was Vera Rubin, decades later, who put it beyond serious doubt. Her patient measurements of galactic rotation curves through the 1960s and 1970s left almost no other explanation possible. By the 1980s, the physics community had begun to take dark matter seriously as a real component of the universe. Planet 9 is a much smaller example of the same essential principle: a gravitational fingerprint left on visible things by an unseen source. The very first confirmed planet outside our solar system was also found by exactly this method. In 1995, Michel Mayor and Didier Queloz measured a small periodic wobble in the star 51 Pegasi. The wobble revealed a Jupiter-mass planet orbiting extremely close in. For that discovery, Mayor and Queloz won the 2019 Nobel Prize in Physics. By now, we know of more than 5,000 confirmed exoplanets around other stars. The overwhelming majority of them were found by measuring some kind of subtle effect on the parent star's light: a wobble, a dimming, a slight shift in position. The planets themselves are almost never seen directly. So even in the study of other star systems, we spend most of our time detecting what we cannot see. By that standard, the Planet 9 question is not exotic at all. It is only the local, closer version of what astronomers have been doing across the galaxy for 30 years. The main difference is scale. Detecting a Jupiter-mass planet close in to another star is easier, in some ways, than detecting a super-Earth at 400 astronomical units around our own sun. That is because the wobble a hot Jupiter causes is small but frequent. It repeats every few days. Planet 9's supposed pull happens over thousands of years, and its signature has to be teased out of the orbits of a small number of extreme trans-Neptunian objects. It is like listening for one very slow drumbeat under everything else. The tools required for that kind of listening are different from the ones used to find hot Jupiters around nearby stars, which is exactly why an instrument like the Rubin Observatory matters. For the first time, we have the survey depth and the multi-year timescale to actually listen for that slow drumbeat clearly. Meanwhile, the outer solar system itself continues to surprise us in smaller ways. In late 2023, a paper by Michael Rowan Robinson reported a possible faint infrared candidate for Planet 9 in old data from the IRAS mission. The candidate was flagged with cautious language, a possibility, not a confirmation. Follow-up work has neither confirmed nor definitively ruled it out. Similar candidates have appeared over the years and largely been eliminated on closer inspection. The pattern of false alarms is normal in a search of this difficulty. Every candidate that gets ruled out is also new information, regions of sky that have been cleared. It narrows where a real Planet 9, if it exists, could still be. In parallel, astronomers keep refining what Planet 9's actual physical properties would be if we found it. Batygin and Brown's most recent papers suggest a body roughly 6 times the mass of Earth. It would be somewhat smaller than Uranus or Neptune, but built more like a super-Earth or a small ice giant than a rocky world like our own. Its surface would be dark, cold, and largely reflective in the infrared rather than the visible. That is one reason it has been so hard to detect. The sunlight reaching it is impossibly faint, and it does not reflect much of what does arrive. It might have a thin atmosphere of hydrogen and helium held onto it by its own gravity. It might have moons of its own, small captured icy bodies orbiting a lonely dark giant. It might even have subtle auroras, generated by any residual magnetic field interacting with the extremely faint solar wind at that distance. But all of this is inference and modeling. None of it is yet confirmed observation. If the world exists, and if we do find it in the coming decade, all of these predictions become testable. That is the state of things. Careful predictions on paper, and a growing search across an enormous but not infinite region of sky. The wider Kuiper belt around it is by now much better mapped than it was in 2016. Thousands of new bodies have been cataloged since the original clustering paper. Most of them are ordinary Kuiper belt objects with modest orbits, well-behaved, unremarkable, and consistent with the classical model. It is only the small subset of extreme objects, those with orbits reaching hundreds of astronomical units, that continue to raise the Planet 9 question. The signal is subtle, and it lives at the very edge of what current data can resolve. In some ways, that is the entire scientific story of the outer solar system in recent decades. Signal, on the edge of what we can measure, waiting for better instruments. Beyond the Kuiper belt lies the far more speculative Oort cloud. It is a hypothesized spherical shell of comets extending out to something like a quarter of a light year from the Sun. No one has ever directly detected the Oort cloud. Its existence is inferred from the orbits of long-period comets, which arrive from all directions and can be traced back to it statistically. If Planet 9 exists, its outer aphelion may bring it into the inner reaches of that theorized shell. The frontier between the Kuiper belt and the Oort cloud, in that case, would be far more populated than we assumed. Even without Planet 9, that outer region is understudied by pure necessity. Objects there are simply too faint and too slow for most survey work. Over the next few decades, that will begin to change. Better instruments will bring at least some of the near Oort population into observational reach. Some of those newly found objects will almost certainly reveal patterns we have not yet noticed. In 2024, Konstantin Batygin and Michael Brown published an update to their statistical analysis, incorporating more than a decade of new observations since the original 2016 paper. The updated analysis found that the extreme trans-Neptunian object clustering pattern remains statistically strong. The odds against random arrangement, they estimated, remain quite low. Their central hypothesis, that a large unseen planet is the most economical explanation, has not been overturned by the last decade of data. It has, though, been refined, questioned, and complicated by parallel work from other researchers. That is science working well. The Planet 9 idea, whatever its ultimate fate, has motivated an enormous amount of new observation of a region we had barely explored. Even if it turns out not to exist, that motivation has been valuable in itself. Astronomy is often like this. An early idea, right or wrong, opens up a region of study that would otherwise not have been visited so intently. The physicists sometimes call this the productive kind of wrongness. It is not a failure to be wrong if the wrongness leads somewhere new. So the coming decade of Planet 9 work matters even in the scenarios where Planet 9 itself is not there. Meanwhile, in the actual now, all the objects that started this story continue on their quiet orbits. Sedna is roughly 200 years away from her closest approach to the Sun. VP 113 is on a similar timescale. Eris, Makemake, Gonggong, Orcus, Haumea, and Charon are all on their long, slow paths through the outer dark. They will all be there whether or not a Planet 9 is announced. Whether we understand them, or their family, or what shapes their arrangement, is entirely on us. The universe does not particularly care whether we solve its puzzles, but it does leave puzzles, patiently, in every direction we look. And the one at the edge of our own solar system happens to be one of the closest we have. For that reason alone, it will remain a compelling piece of work for a long time to come. Because it is close, in cosmic terms. Because the tools to answer it are actually here, or nearly here. And because the answer, whichever way it lands, will change how we understand the region we call home. That is not a small return on a decade of quiet, patient, scientific effort. Even if Planet 9 dissolves into a statistical artifact, or splits into a diffuse ring, or turns out to be a small primordial black hole, or something else entirely, the search itself has been genuinely worthwhile. And if a real planet is out there, and it is found in the coming years, the story simply moves into a new chapter. A named world, at last, in a place we had assumed was empty. Which brings us to the deeper question underneath all of this. How much of the solar system may still be hiding from us? There has been a growing sense, over the last few years, that Planet 9 may not be the only thing hidden in the outer solar system. The extreme trans-Neptunian objects that started this whole discussion are themselves a very small sample. As surveys reach fainter and slower objects, more of them turn up, and their orbits carry information about the region they inhabit. Some of the newer finds have been especially strange, even by trans-Neptunian standards. In 2018, Scott Shepard's team discovered the most distant known object in our solar system at that moment, an icy body they nicknamed Farout. Its formal designation is 2018 VG18. At the time of discovery, it sat around 120 astronomical units from the Sun. That is more than 3.5 times as far as Pluto ever gets. Then the following year, the same team found another object, further out still, at around 132 astronomical units. Well, that one was nicknamed Farfarout, formal designation 2018 AG37, and it briefly held the record for the most distant confirmed object in our solar system. Both were pinkish, icy bodies of a few hundred kilometers across, drifting at distances where sunlight is barely more than starlight. Neither has particularly extreme orbit properties in the sense that would make them Planet 9 markers. But they exist at all in these regions, which pushes our sense of where the boundary of things gets fuzzy. The solar system, in short, does not end where we thought it did even 20 years ago. There are other patterns in the outer objects that continue to raise their own smaller questions. A small number of trans-Neptunian bodies have retrograde orbits. They move around the Sun the opposite direction from everything else. Their existence is a puzzle in itself, since the solar system as a whole rotates one way. Something had to have flipped them, and the mechanism is not fully understood. Others have very high inclinations. Their orbits are tilted almost perpendicular to the classical plane of the planets. These outliers are rare, but they are real, and they carry gravitational histories in them. Every one of them is another small pointer to disturbances we have not yet understood. The sharpness of the outer edge of the Kuiper belt itself is another mystery. The classical belt drops off relatively abruptly around 50 astronomical units, more sharply than most models predict for how it should have formed. Something may have truncated it early in solar system history, a passing star, a large migrating planet, or something else. Or the drop-off may be an observational effect that will smooth out as we detect fainter objects further out. The Rubin Observatory should be able to help settle that question over its 10-year survey. It is a small illustration of how, at this scale, even the sharpness of a boundary is a testable prediction. Then there are the theoretical possibilities that have not been directly detected at all. Some models predict a scattered population of small, Mars-sized or Earth-sized bodies at hundreds of astronomical units, distributed along many different orbits. Not one Planet 9, but many smaller planet somewheres. Each would be individually too faint to have been seen so far, but the combined gravitational effect on the extreme trans-Neptunian objects could still be significant. Distinguishing between one big body and many smaller bodies is difficult from just the current data. That is one of the many things new instruments will help resolve. There is also the ongoing question of the Oort cloud's inner boundary. The transition from the Kuiper belt to the true Oort cloud is not sharp, and the region between them may house objects that resemble neither classical belt bodies nor classical comets. Sedna herself, technically, sits in what some astronomers call the inner Oort region. By that framing, she is not so much a Kuiper belt object as one of the first known inner Oort residents. It is a semantic distinction, but a real one. It changes how we interpret her orbit's origins. The current best explanation for Sedna's orbit involves either an encounter with a passing star very long ago, or the gravitational nudge of an unseen body like the hypothesized Planet 9. Between those two options, and possibly others, the actual answer for how she got where she is remains open. That is a real open question at the edge of our own solar system, in the actual present, with real ongoing work behind it. If a large body like Planet 9 is confirmed observationally, it would not simply be called Planet 9 forever. The scientific community's naming convention for new solar system planets would apply. The name Planet 9 is a working label, a way of talking about the hypothesis, not the world itself. Once a body is confirmed and its orbital parameters measured, it goes through the same review process as any other new solar system discovery. The International Astronomical Union, which handles official solar system nomenclature, would coordinate a formal name. The convention for the giant outer planets is that they are named after Roman gods: Jupiter, Saturn, Neptune. By that convention, Planet 9 might well end up with a Roman mythological name of its own. The discoverers, whoever they turned out to be, would traditionally have significant input into which name was proposed. For now, though, the working name will stay: Planet 9, cautious, understated, and provisional. The classification question would also be revisited. A body of 5 or 6 Earth masses at 400 astronomical units would clearly be a planet by any modern definition. There would be no equivalent of the Pluto debate, since Planet 9 would easily meet all 3 of the current planet criteria. It would have swept its orbital neighborhood, cleared the region gravitationally, and rounded itself under its own gravity. By comparison, Pluto lost its planet status in 2006, in part because it had not fully cleared its orbital region. That decision was made by the same organization, the International Astronomical Union, and it was controversial at the time. It was Mike Brown's own team's discoveries of Eris and other similar bodies that had partly forced the redefinition. In a sense, if Planet 9 turns out to exist, the astronomer who put Pluto out of the Planet Club would be the one to bring in the 9th planet after all. That would be a satisfying arc for a career built on redefining what counts as a planet. Brown, when asked about it, has been publicly amused by the possibility. But the question of whether Planet 9 actually exists remains, as of this recording, still open. In some ways, that continued openness is exactly what makes the search compelling to work on. A resolved question is done. An open question keeps calling for new instruments, new methods, new attention. The Rubin Observatory's 10-year survey is unlikely to be the last effort at this question, even if it delivers a clear result. There will be follow-up campaigns and detailed studies either way. If Planet 9 is confirmed, decades of work will go into characterizing it in detail. Its mass, its rotation, its atmosphere, if any, its moons, if any, its magnetic environment. If it is definitively ruled out, decades of work will go into finding whatever else explains the clustering pattern. Either way, the outer solar system will remain a productive frontier for a long time. The instruments are only getting more sensitive, and the mathematical models are only getting more refined. Meanwhile, at greater distances still, exoplanet astronomy continues to reveal what other star systems look like. Very rarely do the systems we find resemble our own solar system exactly. Most planetary systems around other stars are much more compact than ours, or more chaotic, or dominated by hot inner giants. Ours, with its careful sequence of small, rocky worlds, gas giants further out, and a sparse outer edge, is not obviously typical. Whether it has one more distant giant hiding at 400 astronomical units matters for how we compare our own system to the wider galaxy. That comparison, in turn, matters for how we think about how common systems like ours might be, and by extension, how common the conditions under which life could take hold might be. That is a much larger question than Planet 9, and it does not depend on Planet 9's existence in any direct way. But every new piece of information about our own system's outer regions feeds into it, indirectly. The outer solar system is one of the few places we can study a specific, complete planetary system at close range. What we learn there scales up when we look at other stars. In that sense, hunting for one specific hidden planet is a small part of a much larger effort. That larger effort has been going on for centuries and will continue for centuries more. Any single result along the way, however dramatic, is one step on a much longer walk. That framing is worth holding on to when the media attention around Planet 9 cycles up and down. The story is bigger than the individual planet. Even so, if a real world is out there and we do find it in the next decade or two, it will be one of the more memorable moments in modern astronomy. The discovery of a new full-scale planet in our own solar system has not happened since Pluto in 1930. And Pluto's later reclassification means that in a strict sense, the last confirmed solar system planet was Neptune in 1846. It has been almost 200 years since we've been able to say confidently that our count is now 9. A confirmation now would be that kind of moment, arriving at the end of a decade of careful work. But if the answer turns out to be no, we will have learned something equally important, that the outer solar system is a bit more like it currently seems, and a bit less like the hypothesis suggested, and that some other explanation for the clustering pattern, not yet fully worked out, is closer to the truth. In either case, our understanding will have grown. The instruments will still be there, at 2,682 meters elevation, in the Chilean Andes, watching. The extreme trans-Neptunian bodies will still be there, on their long, slow orbits. The Kuiper belt and the Oort cloud will still be there, still only partly mapped, still holding mysteries. And the human curiosity that started asking these questions in the first place will still be there too, which is, in the end, perhaps the most enduring thing of all. Not any single planet, or the answer to any single question, but the sustained willingness to keep looking for everything that is still hiding, waiting, at the edge of what we can see. So the search will continue, in one form or another, for some time yet. The nights at Cerro Pachón will keep coming, one after another, over the 10 years of the Rubin survey. The instrument will keep gathering data, whether or not any particular result arrives on any particular night. That is how most of astronomy actually works, patient accumulation, over years and decades, with occasional bright announcements woven through. The bright announcements get the media attention. The patient accumulation is where the real understanding lives. If we take a step back from Planet 9 specifically, and think about the outer solar system as it now stands, the picture is remarkable. 20 years ago, we knew of Pluto, of a handful of moons, of a rough, scattered Kuiper belt. Today we know of hundreds of well-characterized bodies past Neptune, including several close to Pluto's size. We have working orbital models that account for the vast majority of them, We have specific open questions that we know how to approach with specific instruments. We have a plausible hypothesis for a large hidden body, actively being tested with real observations right now. None of that existed in this form even a generation ago. In a real sense, we are living through a small revolution in how we understand the outer solar system. It has been happening slowly enough that people not paying close attention may not notice. But look at any solar system textbook from 20 years ago compared to one from today, and the difference is striking. New named worlds have been added. Old boundaries have been revised. The whole outer edge of the map has been redrawn, and it is still being redrawn, month by month, as new observations come in. That kind of continuous change is normal in a healthy area of science. It is when a field stops changing that you should worry. The outer solar system, as of this recording, is very much still changing. There is no particular reason to expect that will slow down in the near future. The instruments coming online in the 2020s and 2030s are much more capable than what existed even at the start of the 2010s. The Rubin Observatory is only the first of them. In the coming years, other new large-scale surveys will contribute their own catalogs. Space-based observatories that cannot easily be built now will eventually be built, and the mathematical understanding of what all the data means will continue to be refined by theoretical work. Each generation of astronomers hands the next a slightly clearer picture of what our home solar system actually contains. That is a real, continuous, cumulative process. It does not require any single dramatic discovery to justify itself. Even so, it would be nice if this particular question, is there really a large hidden planet, could be settled within our own generation. 10 years or 20 years is a small window compared to how astronomy has traditionally moved. But it is not a small window in terms of how the people currently working on it experience their lives. For the astronomers most invested in the question, the search has been going on for most of a decade already. Some of them have made it a substantial fraction of their careers. Others have been drawn in more recently, brought along by the pattern and the possibility. The question has become a small community of its own, with its own conferences and its own regular update papers. Whether that community eventually declares victory or has to slowly conclude the hypothesis was wrong is genuinely open. The atmosphere of that kind of long, patient work is not always what the general public imagines. Most of it is quiet. Most of it involves long stretches of writing and reading and modeling and waiting for observing time on shared instruments. Actual observing nights are, for most of the astronomers involved, remote, done through interfaces to instruments operated by professional staff on their behalf. The romantic image of a lone astronomer at a great telescope, all alone in the dome under the stars, is rarely how things happen now. But the underlying feeling of paying attention to something very far away is still there, in the work. The people doing this work often talk about the calmness of it, how the timescales involved make everyday concerns feel smaller, how looking at objects that will still be there in 10,000 years puts a certain kind of perspective on any single week. That perspective is worth something, even for people who never look through a telescope themselves. It is available, in a small way, from any dark sky on any clear night. The same population of extreme trans-Neptunian objects that started this whole discussion is present, invisible to the eye, in every night sky. So is the region where Planet 9, if it exists, would be. Somewhere overhead, on any given clear evening, is the answer to a scientific question, physically present but observationally hidden. That is a strange kind of poetic fact. Not one that changes much on a practical level, but one worth sitting with. In many older cultures, the night sky was where the important questions lived. That framing is not entirely absent from contemporary astronomy either. The specific questions have changed. The instinct to look up and ask is much the same. Meanwhile, Sedna continues her patient orbit at 100-and-something astronomical units, drawing closer to her perihelion at the pace of centuries. VP 113 does the same, with her own slower rhythm. Eris drifts through the near-classical Kuiper belt at almost 100 astronomical units, one of the largest confirmed dwarf planets. Makemake and Haumea and Gonggong and Orcus and Quaoar all continue their own long orbits. Pluto and Charon are working their strange gravitational dance around a shared barycenter that lies above Pluto's surface. None of these worlds care about our questions, but they are the physical setting for those questions. And each one carries some fragment of the larger story in its orbit and its composition. As instruments get better, more of those fragments will become legible. Some may end up telling us that the outer solar system is simpler than the current picture suggests. Some may end up telling us it is more complicated. Either way, the story is unfinished. That may be one of the truest things one can say about the astronomy of our era. Any story we tell now is a snapshot of a state that will change. There is a small honesty in acknowledging that up front. This has been such a snapshot of where the Planet 9 question stands as of the moment this was made. Details will shift. Numerical predictions will be refined. New observations will arrive, some of them dramatic, some quietly buried in survey catalogs. The overall shape of the question, though, is likely to remain the same for a while. There is something hidden, or something not, at 400 astronomical units. 6 extreme worlds have orbits that either agree or do not agree with each other in a way that either points to something or does not. A large observatory in Chile is systematically watching the region where an answer, of some kind, will eventually reveal itself. That framing will remain accurate for years, and probably decades. It is a strange thing to have a specific, unresolved scientific question that will, most likely, be settled within our lifetimes. Many important questions in astronomy will not be settled in any single human lifetime. The nature of dark matter, for example, may still be open 100 years from now. The origin of the universe, in its deepest sense, may still be open forever. But this particular question, is there a large planet at 400 astronomical units, has a real chance of being resolved within a few careful decades. That is a rare situation, and it makes the current moment somewhat special. In 50 years, the answer will almost certainly be known. In 100 years, it may be part of the standard picture, taken for granted. New questions will have replaced it, some of them not currently visible. That is how the field moves. But for now, in this particular moment, the question is genuinely open. The observatories are working. The papers are being written. The extreme trans-Neptunian bodies are quietly tracing their orbits above your head. And somewhere, if it exists, a cold blue-gray ice giant is drifting slowly through the dark, in an orbit no one has yet directly confirmed. Which is where, for the moment, we can leave the story. The night sky above any of us right now contains, invisibly, the answer to this question. Whether Planet 9 is real, whether the pattern is genuine or a coincidence, the physical answer already exists, physically overhead, whatever we currently think. That is a strange, quiet thing to sit with. It doesn't require any particular belief, just an acknowledgement that the sky is very large, and that some of it is still hidden. The Rubin Observatory will keep collecting light, night after night, on its patient, long survey. The astronomers most invested in the question will keep writing, keep modeling, keep waiting for the data. The extreme trans-Neptunian objects, Sedna and her cold, quiet companions, will keep tracing their long orbits, indifferent to the whole discussion. In 10,000 years, most of them will still be doing exactly what they are doing tonight. In 100,000 years, they will have moved to slightly different points along the same orbits. In 1,000,000 years, most of them will have completed a couple of full loops around the sun. For them, human timescales are essentially imperceptible. For us, 10 years feels like a long window. That mismatch of timescales is one of the things that makes astronomy quietly humbling. It puts things in a certain kind of order. The everyday urgencies, the ones that fill each day and feel very important, stay important on their own scale. But there is another scale where they are not the whole picture. And that other scale is always there, whether we look up to notice it or not. The extreme trans-Neptunian bodies do not care whether a viewer is watching them, or thinking about them, or has ever heard of them. They just do what they do. There is a quiet comfort in that indifference, I think. Nothing about the outer solar system depends on us to justify itself. It has been doing what it does for 4.5 billion years. It will keep doing what it does for a very long time yet, whether or not we ever fully understand it. That is not, in itself, a discouraging thought. It is a kind of steady backdrop. On the surface of any given day, that backdrop is easy to lose track of. But it is still there, patient, whether or not we manage to remember it. Any night sky you have access to is a small opening onto that backdrop. It doesn't need to be a dark sky. Even a moderately light-polluted urban sky shows a handful of stars, if you look. Somewhere in that handful, invisibly, is the direction where these very slow bodies are drifting. You cannot see them, of course, but you know where roughly they are. That is a small, real fact worth carrying. The people who spend their careers looking at the outer solar system often talk about this feeling, how it becomes a kind of quiet company. Even on nights when nothing new is discovered, which is most nights, the field of study is there, populated with real, distant objects. That has a strange gentleness to it. I think about it, sometimes, when I look up from wherever I happen to be, not with any particular training or instrument, just the acknowledgement that there is very much more up there than what my eye can see, and that a small piece of it is being actively investigated right now by people who care. That is a kind of warmth in a place otherwise very cold. Somewhere overhead tonight, Sedna is moving very slowly. Somewhere overhead, the 6 clustered orbital paths are pointing wherever they point. Somewhere overhead, if it exists, a large blue-gray ice giant is drifting through the deep. You can't see any of that, but you know it is there, or you know it might be. Either framing is fine. Whichever framing you carry with you is enough. The details will get sorted out in the next decade or the decade after. And whichever way they land, the story will still be there to be told. For now, though, the sky above you is a peaceful place to leave things. The Rubin Observatory is still working tonight. The extreme trans-Neptunian bodies are still on their orbits. Sedna is still drifting where she has been drifting for millennia. And whatever answers eventually come, they will come slowly, as most real answers in astronomy do. Slow answers are okay. They are, in some ways, the only kind that stay answers. Fast answers get revised. Slow answers get absorbed into the picture and stay there. This whole story has been a slow answer kind of story. That is why it has been possible to tell it in one long sitting. A fast answer story would have been over in 2 minutes. This one has taken a while, because there is a while's worth of thinking to do. Which is fine. The thinking is what makes it worth thinking about. Somewhere, right now, a question is quietly being worked on, by people who care about it enough to spend real years on it. That, more than any single hidden planet, is what I find worth carrying away. The rest is up to the observatory, and to the slow, patient turning of the outer worlds. Rest easy. Good night.